Right, good morning everybody. What I would like to cover is a talk on the edge of architecture and software, at the core of which is composition of blocks. And composition is something that everybody uses the whole time, whether you design hardware or software. I've got two building blocks, F and G, and I can put the two blocks together to do something together. And I can add a result, or I can apply the result of G to F, or I can do something with them. And this is really at the core of hardware and software design. Right? If we didn't have this property, we couldn't design anything that ever worked. And this property gives you the ability to build large systems, complex systems. And if you look at how they differ in hardware and software, in hardware, this property is something that covers both functionality and timing. Right? I take two pieces of hardware that each have one task, and I put them side by side. They perform the same task in the same time. In software, this property definitely covers functionality, but often it doesn't cover timings of the software. And this is a interesting thing that people often take for granted. Right? It's okay that it will run slower if I do the two together, or do one after the other, or I do them simultaneously and go suddenly much slower, or maybe it's not okay. So what I would like to do in this talk is to talk about this principle of composition, and in particular our take on it, and composition of timing. And those of you who saw David's talk earlier will have seen some bits of that already. Before that, I'll just go on multicore real time and how real-time multicore work together. And at the end, I will shortly, briefly show you what it means in practice to have this composition of timing in making fast designs and making designs easily. So, first of all, multicore in real time. This has been around for a long time. People have used different blocks to make things. You put a DSP and a microcontroller next to each other, or a 555 and a microcontroller, or you put three microcontrollers next to each other that together do a task. That is multicore programming. It is a very rigid and rudimentary form of multicore programming. There's no joy in moving from one place to the other. Often you have blocks that perform a function already, and you put those blocks together and they perform a function together. And that has moved on from building on a PCB to building in an SoC. And again, if you look at an SoC, you have all these blocks sitting there together. Sometimes they are programmable multicores, sometimes they are fixed multicores with fixed functions. So we've been doing that for a long time. Now the good thing of using a set of independent devices to implement a function rather than a single ARM core, for example, or xCore or whatever you take, is that independent tasks on independent devices you can reason about, you can divide and conquer, you can implement it, you don't have to worry about it. There's no interference between them. I have a PIC microchip doing one thing, I have a DSP DI doing the other thing, and the two don't talk to each other except when they must. Right? But other than that, they are independent. If you use an RTOS to implement both of the tasks on one thing, it may work, it may not work, it depends on your requirements. And it might be quite difficult to prove that it's ever going to work, or prove that it will always work. Right? So it might be a bit hit or miss. It might work the first instance and not ever again. So the disadvantage of using a set of devices as opposed to a single system is that the set of devices typically doesn't have a communication infrastructure. I have to invent one. I have to use I2C or UART or a memory bus for things to interact with each other. Right? There's no reason why I would put a DSP controller and something else on the same memory bus and use it as a communication mechanism, other than it might be that it happened to work that way. But I'm often inventing a protocol on top of these things that makes it communicate. The other disadvantage is it's often a high integration cost. I have to think at software and at hardware level how to glue these things together. So let's assume we make the microcontroller multicore, which is what XMOS chips are. You can stick a whole lot of cores on one chip. You can stick a whole lot of virtual cores through one pipeline, or you can do a bit of both, right? And it doesn't really matter which one you take. That one is clearly not very economical. That one is quite economical, but might not give you enough performance. And you can scale that one up and make it as high performance as you want. Of course, limited by your communication network here that will at some stage give up and not do what you want to do anymore. So the trick is, you don't need multi-core physical cores. You can use time division multiplexing as long as you do it in such a way that they appear as separate cores. And I'll come back to that later on. Once you accept that time division multiplexing is just a different form of multi-core, life becomes very simple. So, what does the program model look like if I do that? I know I've got a whole collection of threads hanging around, however you want, 8, 32, 128 threads, and the threads are interleaved in hardware by a thread scheduler. I don't have an operating system scheduler, I have a hardware scheduler. They're interleaved as an instruction-by-instruction basis, so I know exactly that each thread will get their fair share, and I can effectively see them as separate cores. They might not be, but to all intents and purposes they are. I can add more cores if I need more performance. Now the interesting thing about this programming model, and this goes back to the composition, is that each thread is now a self-contained unit with time enclosure. I can program that thread to perform a task. I can time enclose it as if I were designing a piece of hardware, and that piece of software on that thread will now have a functionality in a given time, and it will never be different again until I open it up and do something to it and close it again. So if I do that, make a thread, close the timing, I can now compose these threads together and say, here's one thread, here's another thread, now they work together and they do something else, rather than putting them two together and one interrupt will destroy the other. So if two modules work, then the composition works. The second thing you can do, and we'll get back to this as well, is you can embed multiple tasks inside a single thread if the timing allows it. And this allows you to make more efficient use of your threads inside your virtual cores. And we're going to make an assumption here that the threads somehow communicate by exchanging data over their channels. And we'll get back to that as well. So let's first look at how you compose tasks. How simple it becomes. I have two tasks, B and T. They take times TB and TC. And if I execute first B, then C, it takes time TB plus TC. If I execute two in parallel, then the time is the maximum of both. Right? There is nothing that's going to sit in the way of that. What could sit in the way of that? Well, if I implemented that on an RTOS, I could have an interrupt coming along, and the interrupt needs to be serviced, needs to store state, needs to restore state, and suddenly it takes longer than I thought it would. If I implement this on a shared memory multiprocessor, I could have contention on the memory bus, unless I have a multi-ported memory in the way that will help me. If I have locks inside them, one could lock the other one out. I'm in trouble. If I have caches, they could go through the same cache, could destroy each other's footprint. Virtual memory, operating system schedulers, I don't even have to mention. They will just have an enormous granularity and overhead of doing things. So let's go through these. How do we do this? xCore, well, all these resources we talk about are shared inside the physical core. But inside the physical core, we schedule each of the threads one instruction at a go. Hence, they can all take their turn reading or writing to memory. They can all take their turn communicating with and O results. There's no contention on any of those activities. There's no contention on doing anything. The scheduler operates clock cycle by clock cycle, take one instruction, take the next instruction, take the next instruction, next thread, run them through the pipeline, one after the other. If a thread needs to be woken up, it takes a single clock cycle to wake it up. If the thread needs to be put to sleep, it's a single clock cycle. And most important, if I run n threads on an n megahertz processor, each of that gets m over n nips. It's as simple as that. There's no thing taken away from it. Now, interrupts, we mentioned that before. Interrupts are there, but don't program with them. Interrupts fulfill two functions in life. One function is to say something has gone wrong, please give me my attention. The other one is, here's some data, please deal with it. Right? Or can I talk to you, please? Here, deal with it. And these are two separate functions. One of them is important, is dealing with exceptions. We can't get rid of that. So you still do that. And if an exception is that the user has pressed the big red button, it's okay. We can forget about real-time constraints because there is no longer real-time. However, programming with them, like dealing with communication or having a timeout on something or something else simple, you shouldn't really want to do that with an interrupt because you know it's going to happen. And if you know it's going to happen, you should have a different mechanism for it. And a different mechanism is an event. And we'll get back to that. So tasks like that, well, we can now estimate the worst case execution time, which is a normal thing in real-time programming. The difference here is that because we've taken all this contention out of the system, our worst case execution time estimate is going to be a really tight estimate. And it's only going to be bounded by how badly your software is structured. If your software has got lots of if statements and unbounded loops, your worst case execution time is going to be quite unbounded because your software won't allow us to estimate it. If your software is very well structured, the worst case execution time is going to be within a few percent. And it's only down to the software how little that percentage is. And if your software is completely predictable, like a very simple algorithm that just straight line code, the worst case execution time is the best case execution time, is what you know it's going to take. So the good thing about that is that engineering margins are now a thing of the past. You don't need engineering margins in your design. You don't need to say add 10% here, 20% there, 50% there, just in case it's not going to work, just in case all those interrupts happen at the same time. That gives you a tight design, and it gives you an opportunity to minimize the resources to do the task. Now, of course, this is a worst case time. It's not the time that it's going to take. So your computation is probably going to be early. Well, very likely to be early. So if you're going to commit to some performance on I/O, you may have to wait for real time to catch up with you. And this is a common aspect of programming a multicore real-time system. You will wait a lot. You will wait for time to catch up with you. You wait for things to happen because you know they're going to happen. You just didn't know when they were going to happen now or in a few microseconds. Coming back to interrupts and events, one thing you can do, I said, is to take two tasks and implement them in the same thread of control. And very often that is, even a single task doesn't have a single predictable thread of control. Very often a task will be controlling one side and will be listening to something else, and either side might tell me something, and I just don't know who's going to be first. So I might have to respond to an event outside the machine, I might have to respond to another task. I have to respond to either, whichever one happens first. In hardware, it's simple. You have a state machine, two inputs, you deal with both of them. In software, there's that single thread of control. Now, the nice thing of being able to compute this very tight worst-case execution time is that you can now estimate how long it's going to take you to respond to each of those separate events that may happen. You can also compute how long it will take to respond to all of them if they happen simultaneously. And you can, indeed, of course, then work out whether that matches your application or not. Are these three events, they take 1, 5, and 7 microseconds to respond to, do they all happen to be within 20 microseconds? The answer is yes, it will. That's fine, I can deal with all of them. Proven it, ticket, timing closed. So you can now take a compile time decision whether your program is going to work or not, rather than waiting to runtime and then see whether it will work or not. That's great. So how does it work in the xCore architecture? Well, all the resources, that's I/O ports, communications, timers, have events built into them natively. That means there's an event vector that says where the code for this event is. There's a you can enable the events for that resource, and you can tell the thread to wait for whatever event is going to happen next. And if you wait, you stop the thread, and it will vector to the event that's happening at the moment. Now, it's a bit like an interrupt, but there's one big difference. There is this defined place in the program, that wait place, where this thing is going to take place. Because there's a defined place, all my registers will have known values. I can leave known values into them. I won't have to save any registers on taking the event, because I will have saved them in the head already. And I can now straight away deal with the event and get on with life, rather than first having to save context because I didn't know where I took it. More importantly, I'm not in a critical section. I have not interrupted a critical section because I won't put my weight inside the critical section. And if I do, I will do something clever and make sure it is no longer a critical section. So, no need to save or restore. I'm saving clock cycles. I'm saving memory accesses. I've already set up all the registers for different events maybe. Maybe I've split my register set in two for different sets of events. And both the user and the tools can reason about how these events are going to interact with each other and how they're going to interleave. So I can now take two tasks and execute them as coroutines inside a single thread. If I've got too many tasks and too few threads, 15 tasks, I get all of them to wait for an event. The first one to come along, I'll deal with it and go back, and handle with the next one, deal with it and go back. And I keep doing it until I run out of oomph, until I can prove that I no longer have enough time to deal with all those possible events. And at that point, I shan't add tasks anymore. The beauty of that is that these tasks now interact with each other through the shared state in that thread. And there's no danger of the shared state going anywhere. So I create a really simple programming model that's been around again for many years. Event programming isn't new. However, we got a really fast and efficient mechanism to support that. So what does a composable thread look like? This is what it does. I select myself a piece of work to do from the event. I complete that piece of work. It will take me some amount of time, worst case bounded very efficiently. If I'm going to do some time-sensitive I/O, I wait for the right time, and then I perform the I/O, and I get on and with step one. Now, that one is easy. That one is easy. The second task, we know exactly how long it's going to take, and the only thing we have to make sure is it's fast enough. And if it isn't fast enough, put a faster processor in, split it in two, and if it's still not fast enough, use somebody else's chip. Stick an FPGA and do something else, right? But at least you can, at compile time, say it's going to work. Right? You don't have to wait and engineer the whole platform. The difficult bit is step 4, because that is where you interact with the rest of the system. That is the place where actually I might have two tasks that want to talk to each other now and then. I want to exchange a message. And this is the bit where real-time programming suddenly could give up, because I could be too early or the other one could be too late, and they will wait for each other, and here's an unpredictable amount of time I have to wait. So we've pushed all the hard bits into that one step. And that one step is now your contract between the separate individual threads to say how they will interact with each other. Each thread has a contract that says, I'll respond this fast to a request that I get. I'll respond within that time. So it is still a hard bit, but at least it's all within the one place, which makes it manageable. So I want to give you a short case study. There's only 2 slides on this case study, so don't be afraid. Just something I did. I took 2 existing designs that XMOS used to have lying around. One was something that took one network USB, and it sent audio over that, and the other one had another network and sent audio over that, and there were 2 completely different standards, one implemented completely different organizations worldwide. And I was wondering whether I could take those 16 tasks, those 20 tasks, cut a few bits out here and there, reuse the important bits, and create a combined one that would simply interface audio over Ethernet with audio over USB. So rather than having two devices that talk to a speaker and talk to a microphone, I took the both audio halves out and wanted to glue them together and say, here we go, we got USB interface to Ethernet. Real-time USB to real-time Ethernet, right? Not just simply, here's a bridge that does it a bit. No, it's actually doing the real-time part. So, remove half of that one, the bit you don't want. Remove half of that one, the bit you don't want. Stick a buffer in the middle, and job done. The beauty of it is that it took me 3 hours to do this. I had to study the AVB code because I've never seen it before, which takes a little bit of time. And you realize which bits you don't need, and you remove them from your source code. You glue the other part into it. You use cover because it's C, the two variables, both have the name count, and both global, so it doesn't work. So you have to do a wee bit of editing here and there to make that work. That was a bit nasty. And you make it compile, and after that, you remove the trivial errors, and then it works. Good thing was I knew the USB software inside out, so I didn't have to study that. And of course, it takes more than 3 hours to make this a bomb-proof piece of software that you can sell. However, making a demonstrator out of two real-time platforms and gluing them together in 3 hours is only possible because all those components, all those 16, 20 tasks that comprises these two tasks were all timing closed in themselves. So I didn't have to worry about any of that. I just took the bits that I wanted, I re-implemented the contracts on the edges, and off you go. So, composition is really important, but timing is even more important. And everybody doing hardware will know that. Very few people doing software will appreciate how easy life is if you don't have to worry about timings. Right? So, composition of threads and events, you can really quickly knock up a new system. And it is a way of adapting and reusing existing bits. That's it. Any questions? No? Good. Thank you very much.